Welcome back. In this video, we are going to cover the last chapter of this course about complete matrix spaces. This is a very short chapter. So let us start by defining completeness. Okay, in order to define completeness, we need to define the notion of a Cauchy sequence. What is a Cauchy sequence? And why is it important? Consider first a convergent sequence in a matrix space. Okay, xn that converges to x. And we know by now that what does this mean? This means that so the distance between xn and the limit can be made arbitrarily small, so less than any positive number if n is large enough. Okay, so if we take two indices n and m that are larger than n0, then the triangle inequality implies that the distance between xn and xm is less than 2 epsilon. So it can be made arbitrarily small. Okay. So now, if we wanted one exactly epsilon here, we should have taken epsilon over 2 here, but this is not important, as we know. Okay. So now a sequence. So any convergent sequence satisfies this property that the distance between any two terms with large indices can be made smaller than any positive number. A sequence having this property is called a Cauchy sequence. Okay. So, and there are other ways to rephrase this condition. So one way is to say that limit of dxn xm as nm tend to infinity is 0. Okay, so this is the definition. If xd is a metric space, a sequence xn of the space is called a Cauchy sequence. If for every epsilon positive, we can find a certain rank n0, starting from which the distance between any two terms of the sequence is less than epsilon. Okay. Now, of course, we can write less than epsilon or less or equal than epsilon, doesn't change. Okay, so we know by now that any convergent sequence is a Cauchy sequence, okay, by the triangle inequality. Now, what about the converse? Converse need not be true. We shall give some examples. If the converse is true, we say that the space is complete. Okay, so metric space xd is said to be complete if every Cauchy sequence of x is convergent. Okay. Now I'll give examples of complete and non-complete metric spaces. Okay. So completeness is a metric property. It's not a topological property. So first example, Q is not complete. Why? Because if we take the sequence of rational numbers converging to radical 2, 1.4, 1.41, and so on, this is a sequence of rational numbers. We know that it's a Cauchy sequence because it converges in R in the bigger space R. But for people who live in Q, radical 2 is not in their universe. Okay, so for them, this is a Cauchy sequence, but it's not convergent. Okay, it's convergent to something outside their universe. So Q is not complete. However, R is complete. Okay, another trivial example. If we take a sequence the sequence xn defined by 1 over n, so 1, 1/2, etc. This is a sequence that we know that it converges to 0 in R. So it's a Cauchy sequence. But the limit is 0. It's not in the universe 0, 2. So the open interval 0, 2 is not complete. Okay. And so this is an example that shows that completeness is not a topological property because 0, 2 is homomorphic with R, and R is complete, whereas 0, 2 is not complete. Okay. Now, as you said, there are two other ways to formulate or to rephrase the Cauchy condition. So xn is a Cauchy sequence if and only if the limit of dxn xm as both n and m tend to infinity is 0, or if you like, if you write m as n plus p, then for every pn, and the limit of the distance between xn and xn plus p as n tends to infinity is 0. Same thing. Okay. As you may easily check. So you can use any one of these. So I have three ways of rephrasing the Cauchy condition. Okay, now let us establish some elementary properties of Cauchy sequences before we prove that R and Rn are complete. So first of all, a Cauchy sequence is bounded. Okay, we know actually that every convergent sequence is bounded, but in general, a Cauchy sequence is bounded. Why? Because if xn is a Cauchy sequence of a metric space xd, and we take epsilon equal 1 in the definition of a Cauchy sequence, then we find an index n0, starting from which the distance between any two terms is less than 1. 1 is enough. Okay, now consider the set of all distances between xn and xn0 for n less or equal than 0. This is a finite set. So we take the maximum. Now, we distinguish between two cases, n less or equal than n0, n bigger or equal than n0. If n is less or equal than n0, then by definition, the distance between xn and xn0 is less than the maximum. So it's less than m, and so it's less than m plus 1. However, if n is bigger than n0, then according to our choice of n0, the distance between xn and xn0 is less than 1, and this is less or equal than m plus 1. So in all cases, the distance between xn and xn0 is less or equal than a constant m plus 1 for every n. So this means that the sequence xn belongs to the ball, the closed ball of center xn0 and radius m plus 1. So this set is bounded, so the sequence is bounded. Okay, second lemma. Pay attention. If a Cauchy sequence contains a convergent subsequence, then the original sequence is convergent. Okay, this is not true for any sequence. Okay, so we have two conditions here. Xn is a Cauchy sequence and it has a convergent subsequence. Oh, this is not difficult. Consider a convergent subsequence xni, if you like, xni, that converges to some x. We want to prove that the whole sequence xn or xi, if you like, converges to x. So let epsilon positive be given as usual. Then by definition of convergence, there is an index m1, starting from which dxni, the distance between xni and x, is less than epsilon over 2. Okay, for I bigger or equal than m1. This is just the definition of convergence. Now let us try the condition of the Cauchy condition. In particular, if now the distance, so there exists a certain rank m2, starting from which the distance between any two elements of the sequence is less than epsilon over 2. So in particular, if I take I to be greater than this index or equal, and since ni is also bigger than I, if I is bigger or equal than m2, then ni is also bigger than m2. Okay, so if you take n0 to be this m2 in the definition of a Cauchy sequence, then both ni and I are at least m2. So their distance is less than epsilon over 2. And now we just have to use the triangle inequality to conclude that the distance between xi and x is less than epsilon for every I which is both bigger than m1 and m2. So this proves that the original sequence xi converges to x. Okay, now first corollary, a compact metric space is complete. This is trivial. Why? Because we know that a compact metric space is sequentially compact. So if xn is an arbitrary Cauchy sequence of a compact metric space, then xn sequential compactness tells me that xn has a convergent subsequence. But according to the previous lemma, the whole sequence, the original sequence, is convergent. So compact metric implies complete. Of course, the converse is not true. Rn is complete under any one of the usual distances that we defined in chapter 1. Okay, proof. So consider a Cauchy sequence in Rn. Then we know that by the first lemma, the sequence is bounded. So it belongs to a closed ball, and the closed ball is compact, as we know. So sequential compactness tells me that this sequence has a convergent subsequence, and according to the lemma, the original sequence is convergent. So we started with an arbitrary Cauchy sequence in Rn, and we proved that it is convergent. Okay, so this is very important because why do we are interested in completeness and Cauchy sequences? Because if we want to prove that a sequence is convergent, we have to know first the limit. Okay, the Cauchy criterion, if the space is complete, then we don't need to know in advance the limit. We just need to prove the Cauchy condition. Okay, so completeness tells me, and we shall give an example that illustrates the use of completeness in a moment. Okay, so we have when we work in complete metric space, we have another way of proving that a sequence is convergent without knowing the limit in advance. Okay, so this is important, especially in some theoretical considerations, and I will give one illustration of this in the Banach fixed point theorem. Okay, now before we move to the Banach fixed point theorem, let me just mention an important result. If XD is a complete metric space and F is a subset of X, then F itself is complete if and only if it is closed. And this is pretty straightforward. So suppose that F is complete for the distance D. We have to prove that F is closed. How do you prove that? Prove that it's equal to its closure. And how do you prove that? You take an element X in the closure and you prove that it's an F. So if X is an F bar, then by proposition 1.8, there exists a sequence Xn of F that converges to X. Okay? Therefore, in particular, Xn is a Cauchy sequence in F, but F is complete. Therefore, the sequence converges to some element Y in F. But the sequence converges to X by definition. So, therefore, by uniqueness of limits, X equal Y, and therefore X is an F. This is half of the implication. Okay. Now, conversely, suppose that F is closed. We want to prove that F is complete. So we take an arbitrary Cauchy sequence, Xn and F. Okay, but F lives in a complete space. So Xn, therefore, Xn is a Cauchy sequence in the complete space X. Therefore, it has a limit X. Okay, so Xn converges to X, but X must be in F bar. But since F is closed, F equal to F bar, and therefore X belongs to F. Therefore, the sequence Xn converges to an element in F. Okay, so when we talk about completeness, the limit must be in the space. Okay, and now we come to the Banach fixed point theorem. And before we formulate it, let us give some definitions. If X is a set and F is a map from X to itself, it's important that F be a self-map. A fixed point of F is a point such that which is invariant under F. So A is equal to its own image. It's a fixed point. So it's like the center of a rotation, for example. Now, not every map has a fixed point. Okay, for example, translations do not possess a fixed point. Okay, first definition. Second definition, contraction. In general, if you have a map F between two metric spaces, we say that F is a contraction if it is a Lipschitz function or Lipschitz continuous function with constant strictly less than 1. Okay? So the distance between the images of 2 points is less or equal than a certain constant less than 1 times the distance between the original points. So in other words, F shrinks distances, contracts. This is the origin of the word contraction. Okay. For example, if you consider the map F from -1, 1 to itself, given by x squared over 3, you need to check that if x is between -1 and 1, then x squared over 3 is actually between 0 and 1/3. So, of course, it belongs to -1. So this is a contraction. There are several ways to prove that. The most general way is to use the mean value theorem, because F is differentiable and F prime is 2/3 x. If x is between -1 and 1, it means that in absolute value x is less than 1 or equal. So F prime of x is less or equal than 2/3. And so by the mean value theorem, f of x minus f of y is less or equal than 2/3 x minus y. Okay, here we are taking the usual distance on -1. Okay, so f is a contraction with ratio 2/3, which is less than 1. And here's the final and central result of this chapter, the Banach fixed point theorem. If X is a complete metric space, and F is a contraction, then F has a unique fixed point. Okay, so we have actually several assumptions here that we have to pay attention to. First assumption is that X is complete. Second assumption, F maps X into itself. It's very important, and I will go back to this later. Okay. So the target space and the source space must be the same. Okay, and F is a contraction. So in particular, it's continuous, of course, because contraction means Lipschitz continuous, means uniformly continuous, means continuous. Okay, now, the proof is not very difficult, okay, but it illustrates the use of completeness. Okay, let us prove first the uniqueness part. So F is a contraction, so by definition, there is a constant k less than 1. such that the distance between f of x and f of y is less or equal than k times the distance between x and y for every xy in the space. Okay, suppose that f has two fixed points, a and b. Then if I apply this fundamental inequality, I replace x by a and f and y by b, I get that the distance between f of a and f of b is less or equal than k dab. But a is a fixed point, so f of a equal a. And b is another fixed point, so f of b equal b. Therefore, I get d of ab is less or equal than k dab. Okay, so if you subtract, you get 1 minus k dab is less or equal than 0. And the fact that k is less than 1 strictly implies that necessarily dab is 0, because otherwise dab will be strictly less than itself. So a equal b. Okay, now we prove the existence of a fixed point. So this is a fundamental iteration analysis. So we start with an arbitrary point A, okay, or x0 if you like. And we define a sequence by induction. So we set x0 equal a and xn plus 1 equal f of xn. So this is just an iteration. So a, f of a, f of a, and so on. So this is, we get a sequence now that we call actually the orbit of x0 under f. Okay, now we have to we'll prove that xn actually is a Cauchy sequence, and then we'll prove that the limit of this sequence is the required fixed point. So let us first evaluate the distance between xn plus 1 and xn. So we replace xn plus 1 by f of xn, and xn by f of xn minus 1. Okay, and we apply this inequality. The distance between f of xn and f of xn minus 1 is less or equal than k times the distance between xn and xn minus 1. So therefore, if we repeat this by induction on n, so if we apply the same inequality to dxn xn minus 1, we get that this is less than k times dxn minus 1 xn minus 2, and so on. So after n steps, we get that xn, the distance between xn and n plus 1 and xn is less than k to the n times the distance between x1 and x0. Okay. Now consider an integer p bigger or equal than n. This estimate, by the way, does not prove that xn is a Cauchy sequence. Of course, the distance between xn plus 1 and xn tends to 0. But this is not the Cauchy condition quite, okay? Because the Cauchy conditions says that the limit of xn plus p and xn tends to 0 as n tends to infinity. So I need to prove another estimate actually, but I will build on this estimate. Okay, so if you prove that the distance between xn and xn plus 1 tends to 0, this does not mean that xn is a Cauchy sequence or that it's convergent. You can give counterexamples. Okay, so but now to prove that it's a Cauchy sequence is easy, because this is just the consequence of the triangle inequality. The distance between xn and xn plus p by the triangle inequality is less than the distance between xn and xn plus 1 plus distance from xn plus 1 and plus 2 and so on, up to distance of between xn plus p minus 1 and xn plus p. So now if we apply the previous estimate, the first term is less than k to the n distance from x1 to x0. The second term is less than kn plus 1. Okay. Just and so on. The last term will be less than kn plus 1 plus p minus 1 times the distance. So we have dx1 x0 in common, and we can factor by this geometric series. And now, of course, if we factor by kn, this is just a geometric series, so you'll convince us, as you know from school, this is just kn times 1 minus k to the p over 1 minus k times the distance between x1 and x0. And since k is less, so since k is bigger or equal than 0, 1 minus k is less or equal than 1. So the distance between xn and xn plus p is less or equal than kn over 1 minus k times dx1 x0. Now, dx1 x0 is a constant, 1 minus k is a constant. As n tends to infinity, this tends to 0 because k is strictly less than 1. So the distance between xn and xn plus p tends to 0 as n tends to infinity, and this proves that xn is a Cauchy sequence. And now I use the completeness of x. Since x is complete, xn has a limit n. And now this would be my fixed point, because I know that f is continuous. So if I look at the equation xn plus 1 equal f of xn, and let n tend to infinity, xn plus 1 tends to L, and xn tends to L, so f of xn tends to f of L. Therefore, at the limit, I get L equal f of L, and therefore L is the required fixed point. And yeah, this ends the proof. Now, two remarks. As we mentioned, it's essential that f maps the space into itself. Okay, why? First, because if x is a fixed point of x, then x is equal to f of x. So x and f of x should belong to the same space. Okay, but even if x is contained in a bigger space y, and f is a contraction from x to y, f need not have a fixed point. Here's an example. If you consider the map f from 0, 1 to 0 radical 2 given by a radical of 1 plus x squared, okay, check that this is a contraction but has no fixed point. Take a paper and a pen and check what I'm saying. Okay, so it's very important that we have a self map. Okay. Second remark, of course, a contraction has at most one fixed point because, as we said, by the uniqueness part of the proof. Now, completeness is also essential. If you remove it, the theorem may go wrong. So, for example, take the set of rational numbers that are between 1 and 2 and equip it with the usual distance. And consider the function f of x given by x over 2 plus 1 over x. Now, you may check that f is a contraction from x to itself, but it has no fixed point. Why? Because the fixed point is radical 2. It's not in x. So once again, take a paper and a pen and check the details. It's very instructive. So you have to pay attention to all the assumptions. If you remove one assumption, you have a risk of losing the conclusion. So this concludes chapter 5 and the course. So I still need to solve the exercises in the next video. So thank you for your attention and see you next time.